actually more geared towards answering the last question or directed in that direction. As it's been said, I work in causal inference primarily because I'm a member of the Biostatistics department at Harvard, and I interact with epidemiologists. And the field of epidemiology in itself, its major goal is to understand the determinants of disease, the treatments, agents, exposures that cause or can prevent disease. And the goal there is to somehow provide guidelines to effective interventions to prevent or fight disease. Now, the gold standard of this kind of analysis is the randomized trial, because in randomized trials, treatments are randomly allocated and trials don't suffer. This randomization prevents the selection biases that naturally occur in observational studies. But randomized trials are often unfeasible for a host of reasons. They are costly, they are impractical, or they are unethical. So most of epidemiologic work is based on observational studies. So how do normally epidemiologists analyze observational studies? Well, they try to emulate a clinical trial, a randomized trial. How do they do that? They assume that within levels of baseline covariates, there is essentially a randomized trial going on. Now, in order to do that, they have to assume that, or they have to collect enough covariates so that the covariates that they recorded are the pool of covariates that include all the determinants of disease and predictors of exposure. Now, of course, nobody, this pool is enormous and it's unclear what it is. So one of the major goals, the major challenges of epidemiologic work is to recognize, to gather enough covariates or confounders to control for this possible selection bias. So traditionally, epidemiological studies were based on following cohorts of individuals, either prospectively or retrospectively. Now, in the new generation, with the advent of new data, especially data coming from health insurance claims, electronic medical records, national registries, there's a all new set of data that was not designed for research purposes, but that is available to furnish additional valuable information that allows now epidemiologists to have a much bigger pool of variables from where to select confounders, these covariates that I just mentioned that allow us then to pretend that we can emulate a clinical or a randomized trial. So one big challenge that nowadays epidemiologists face is, okay, now we have lots of covariates, now we have data that is very rich in variables, in potential confounders, but we just can't use all of them because most of the time the covariates, the number of covariates is almost of the same size as the sample size, so, or even bigger. So we have to do some kind of variable selection. And how do we face that challenge is essentially what a lot of activity in causal inference is going on in these days. So what I would like to do is to explain a little bit in this talk some of the challenges for variable selection when p, the number of variables, is much bigger or scales with the sample size. As we will see, the formal problem is to conduct inference about a finite dimensional parameter. So here, really, in causal inference, we really want to test, to do inference to estimate a parameter which has a causal interpretation, but we have a high-dimensional nuisance parameter. Usually, it's a function of these covariates that we need to select. In the past decade, as I said, there was a well-mature literature on confounder control methods, assuming p is fixed and n is large. In other words, making all the theory and the asymptotics, assuming that as n gets larger, the number of covariates remains the same. But that theory doesn't really fit or suits the need or the need for analysis with large number of covariates. So in this decade, there has been a rapid growth of methods that actually adapt the past decade methods or techniques by incorporating machine learning methods to estimate that big nuisance parameter, high-dimensional parameter, and at the same time handling the large number of covariates. So today, what I want to do is first review some key points of this new generation of methods. And here, my presentation actually will borrow from a recent archives article by Chernosukov. Chernosukov is an econometrician because actually there's a whole area of econometrics that pretty much does the same as, or focuses on the same kind of problems as causal inference in epidemiology. That's what's called program evaluation. And the econometricians have made a big progress, and the two fields really touch each other. So what I will be talking about really is about recent progress in both fields. And then at the second part, I want to present some work of my own, where I will, just by introducing this work, I will show a little bit of an area that I believe has not been carefully taken place in the discussion. So here is the outline. Now, I will start by motivating the discussion with very, very simple examples, perhaps the simplest, most basic element in causal inference called the average treatment effect. And then I will try to explain why naive plug-in methods fail in high dimensions. This is, I'm not going to say anything new. It's something that is well known, but perhaps to this audience, it will be helpful to understand what's the problem with variable selection. Then I will talk about the role of influence functions in the bias in naive estimators, the role of cross-fitting to alleviate smoothness requirements. And finally, these 2 points, 1 through 4, are pretty much what I said is in Chernosukov, but then 5 and 6 is what I will add from my own work. So, OK, so motivation with ATE. So this here I'm following pretty much, work, a famous paper by Lev and Poster, also a reviewed in some sense in a different context by Belloni. So we have a treatment, T, that I will assume it's binary. And we have an outcome, Y. And we have a large set of confounders. X is a huge set of confounders, or covariates. And let's say that we write Y as the mean, given T and X, plus error, and T as the mean, the treatment, the mean given the covariates and the error. Now, in causal inference, the parameter of interest, one parameter of interest is what's called the average treatment effect. And formally, that average treatment effect is the difference of means. But which means the mean of a mean of the outcome given only conditional on the treated and the confounders, but then average over all the confounders, minus the same mean, but now taken on the subset of the people that are not treated. So why is that of any interest? Well, that dates back to what's called the Rubin causal model, where we envision two counterfactual, two potential outcomes. One, where an individual, this is the outcome, where the individual, that we will see if the individual were not treated, and Y1 is the outcome if we were to see the individual, if the individual was treated. Now, the big assumption of unconfoundedness says that, essentially, within levels of X, D should be T here, sorry, this should be a T. T is as good as randomized. What it means is that we can pretend that within levels of the confounder, within levels of X, the assignment of treatment was at random. And if that was the case, then the treatment that a person receives should not depend, should be completely independent of the outcome that the person would have if the person were treated or the person were not treated. Now, under the assumption of unconfoundedness, and the assumption that everybody has a chance of receiving either treatment or control, and the assumption that whenever we see an outcome of a person that was treated, that outcome corresponds to the potential outcome, and vice versa, then it can be easily seen that the mean in the world, if everybody was treated with T, the mean of the outcome in that world would be exactly the mean of the conditional mean of the outcome, given that the person was treated with T and X. Okay, so this object here, it's a statistical object, is a parameter that it's very much of interest because that tells me what would happen in the world, what would be the average outcome if everybody in the world was treated with T. Okay, of course, there's three assumptions there, and the most important one is unconfoundedness. But in order for that assumption to be true, we need to have X, a big subset, and we need to select the X's properly, okay? So that's the challenge, okay? So what I will do is I will discuss briefly the problems with estimation, what the real practical problems one faces with estimation of a quantity like this one, okay? So, a natural way to estimate this parameter would be simply to say, well, let's get an estimator of the mean. Remember, this is the mean of the mean, okay? So why don't we estimate the mean of the outcome among people that were treated, okay? And conditional and covariates, we estimate this, and then we take the sampled average over everybody, and that's it. That's our estimator. Well, as you will see in a minute, that simple estimator has problems when we are in high dimensions. What is the problem? Well, to think about the problem in high dimensions, I will actually make it very simple to show you the problems. I will actually make it very simple and think of one dimension, okay? So I will just think of X being a univariate, okay? Just a scalar covariate, okay? And suppose that the model, the true model for the mean of Y given T equal 1 and X is beta 0 plus beta 1X, the simplest possible model in the world. But suppose that to estimate G, you do something dumb, but not dumb because it replicates what it's being done in practice in large dimensions, which is you select. You decide whether you're going to include X in your model, in your fitted model, by pre-testing, by doing a test where you do a t-test, you reject, or because we then sample size large enough, you reject when the t-statistics is greater than a critical value. And in that case, if you reject it, your estimator of the mean, oops, I think it's not working. Your estimator of the mean will be just the predicted value from the regression. But if you fail to reject, you are just going to estimate G with just the sample average of the Y's of the outcomes among the treated, okay? You are doing this just for the treated individuals. This is what you would normally do and what it's, in fact, replicate in common practice. What do we normally do? You know, what practitioners do in epidemiology? They have lots of covariates. They just test covariates. They just select a smaller model and just report that model, okay? Report the results of that model. Think that now we are just doing that. We are reporting the model, but we are averaging over all the covariates, okay? Well, it turns out that with lots of covariates, if we wanted to do a selector method or an automatic selector, Lasso will be an automatic selector, and Lasso will actually act in this context very much as a conservative test with an alpha level of 1 over n. Okay, so that's a fact. That's how Lasso acts in just one dimension. And then with this choice, the critical value actually feels or behaves like the square root of 2 the logarithm of n. So the test will reject, this preliminary test will reject every time the size of the ordinary least squares parameter of the beta 1 is greater than a constant, the constant being the standard error of the error divided the standard error of the covariate, times square root of 2 log n divided by square root of n times some insignificant term. Okay, plus some insignificant term. So what's the issue with this? Okay, remember, this is how Lasso, or how we would be doing in high dimensions if x was rather than 1 dimension high dimensions. This is the equivalent of what we would be doing. Selecting covariates and then using those covariates to estimate the regression model, okay? So here is the problem. So suppose that beta 1, okay, that beta 1 was, say, for example, 2 times the square root of log n over the square root of n. Well, that's twice as much, or, well, not twice as much, square root times as much as the critical value. But that's a lot, okay? It's much more compared to the variability of beta hat 1 of the OLS, and therefore, essentially, the test will be rejecting with probability going to 1. Okay, so if the true beta 1 was around here, no problem. The test will always select the beta 1, and the estimator of the coefficient, the parameter of interest, will just be the average of the OLS fitted with both beta 1 and beta 0 and beta 1. In that case, it's clear that the estimated parameter minus the true value, appropriately scaled by square root of n, will actually be asymptotically normal, center, everything will be fine, okay? Now, on the other hand, if beta 1 was of order smaller than 1 over square root of n, that will be very far away from the rejection region, and essentially with probability 1, all the beta hat 1s will fall in the acceptance region, so we will be always accepting, failing to reject, and our estimator of theta tilde will just be the average of the outcome among the treated. But if that was the case, then it's easy to write down a short calculation, short algebra, will show that now the expression for our estimator minus the parameter that we want to estimate will have 2 parts. A part that will behave nicely, which will be the empirical mean of the errors among the treated, multiplied by square root n. That behaves nicely. And then there will be this part here, that will be the square root n times the coefficient, the true coefficient beta 1, times the average of the covariates in the treated minus the average in the entire population. Now, remember, we would like to make this be zero random variable, essentially, or going to a normal distribution with mean zero. And of course, if beta 1 was of order smaller than 1 over square root of n, square root of n times beta 1 will go to 0, and this will vanish, and we will have a normal distribution. More so, it will behave, this estimator will behave as if it was discarding the unnecessary covariate, because x will now not really be necessary for controlling for confounding, since the beta 1 is so small that really x has no impact on the outcome. But what happens in an in-between situation? What happens if beta 1 now is square root of log n over square root of n? It's not as small as little o of 1 over square root n, or not bigger on this area. It's in the middle, but growing or decreasing at the rate square root of log n over square root of n. Well, in that case, it's clear the test will be always failing to reject, but then the estimator now, again, will be the average of the outcomes among the treated. The problem now is that the square root n times beta 1 will now be a constant times the square root of n. And now it's a problem, the square root of log n. Now it's a problem because if the covariate x is truly needed for controlling for confounding, which means that the mean of the x's, the mean of the covariate among the treated is different than the mean of the covariate and the whole population, that is, there is no balance in the baseline covariate, then this term here will not vanish, will go to a constant, and this will explode to infinity, okay? And in that case, then, what will happen is that this expression here will tend to infinity. We will not have a center estimator. We will not have an estimator converging to a normal distribution. Now, let me emphasize, this is not something unknown. This is something that is well documented and well known for lasso selectors. They are too good to be true because they are actually super efficient in certain areas, but actually have very bad behavior in some other areas. But of course, we don't know where we are when we do testing. So if we do testing and we just happen to be in such a bad luck that the true parameter beta 1 is here, our inference about theta will be completely erroneous, okay? Will be badly and erroneous, okay? So this theoretical analysis actually has a lot of implications in practice, okay? Just doing variable selection pre-testing, it's a problematic strategy. Okay, so here is a situation with multiple, in high dimensions. I take the number of covariates equal to 1,000 and the sample size equal to 1,000. And I generate X to be a multivariate normal with a Toeplitz correlation structure. And I generate G1 to be a very non-sparse function of X, okay? It's a regression function which has coefficients decreasing to 0, but at a very slow rate, okay? And then I take the propensity score, the probability of treatment given X, to depend on the first two covariates. So these two covariates are actually confounders, right? Because they predict treatment and they predict the outcome within levels of treatment. All right, if I just do G hat, or if G hat is the ordinary least squares, select on the covariates that were selected by Lasso with cross-validated tuning parameters, and then I replicate this. I do simulations, 1,000 replications of these simulations, and I calculate on each replication the estimator, theta tilde, the plug-in estimator that I just described. I get this distribution, when the true parameter is 0. Okay, so we see here exactly the effect that I just described. Okay, the estimator is not centered at the true parameter value, and if I were to do inference about theta, I will be completely wrong. Okay, my inference will be wrong, my confidence intervals will be wrong, and so forth. Okay, so what I want to do now is to show a whole array of ideas. I mean, basically, it's one idea that pretty much is behind all the methods that debias or that handle the high-dimensional covariates. So here is the idea. Suppose that the true model for pi, for the expected value for the propensity score, the probability of treatment given the covariate, was actually a logistic regression, again, in small dimensions, with some coefficients gamma 0 and gamma 1. And suppose that we also do lasso, we do variable selection on gamma 1, okay? So remember, X is high dimensional. We are going to do variable selection on the outcome regression, but now we are also going to do variable selection on lasso. Okay, so if we do that, again, our estimator of the propensity score will be the x-bit, the x-bit of the whole regression if we fail, if we reject, if the test rejects. But otherwise, will be just g of the estimator of the intercept with just the average or the proportion of treated in my sample. All right, if I do that, now I can consider a new estimator, which is an estimator that will try to debias the original estimator. Remember, this was theta tilde was the estimator that I just showed you has bad bias, is badly biased. And now I'm going to add to that an estimator of the bias. So what do? I just take, for every person that is treated, I take the outcome that I've seen, and I subtract what I estimated the mean of the outcome for that person should be. But I now weight that difference, which gives me an idea of the bias. I weight it so that each individual that was treated represents all other individuals like him that were not treated. Now, this adjustment here is very well known. This new estimator, that it's the original plugin plus the adjustment, is very well known, and it's been around for a long, long time. In survey sampling, it's referred to as the Calibrated Estimator by DeVille and Sarnal. In Causal Inference, we worked out this estimator proving semi-parametric efficiency for estimating that parameter theta a long time ago. But it's a well-known estimator. So what's the issue with this estimator? Let's try to see what happens. All right, so first of all, let's try to see how this estimator will behave when the lasso estimate, the selector, selected beta 0 and beta 1. In other words, we fitted the big model. Well, when we fitted the big model, this random variable here will be essentially a normal random variable because y minus g is center. It has mean 0. So this will be a random variable behaving very much like a mean 0 normal distribution. So the big issue is, how does this adjustment, what does this adjustment do when actually we failed to include x when we should have included, okay? So here is the deal. The estimator, the new estimator minus theta times square root of n, can now be shown to be some term that it's bounded in probability. And now the debiasing, adding this beta n, the actual effect was just to add a term to the bias term, okay? This delta hat n, where delta hat n is actually, if you look at this, it truly looks like an estimator of x bar t minus the expected value of x. It's actually an estimator of this difference, but with a minus sign. because this is an estimator of the mean of x, and this is an estimator of 1 times x bar t. Okay, so this should act as minus this guy and should cancel out the bias. Okay? Now, but remember, we were going to do variable selection on pi hat as well. So when we selected x for pi, we are fine because we have a consistent estimator of pi, and truly, this whole expression here, square root n times this, behaves like a normal distribution. So I have beta 1 times something that is of order 1, but beta 1 was converging to 0, so this bias term goes to 0, and everything is fine. The most interesting case is what happens when the lasso didn't select the x for pi and didn't select the x for the outcome regression. It didn't select it for both. Well, in that case, delta hat n is actually equal to 0. It's truly equal to 0. Okay? So if delta hat n is equal to 0, we are back to the old guy. We have beta 1 times square root n times the bias term. But the key insight is that actually lasso will fail to select x for pi precisely in those regions where x is not an important confounder. So in those regions, x bar t minus e of x will actually be a small order. In fact, x bar t minus the expected value of x is of the order gamma 1, the order of the parameter that we are, of the covariate corresponding to the covariate that we are failing to select. So in that case, what happens now is that the bias term would be square root n, beta 1, gamma 1 times an OP1 term. But now, because we failed to select both beta 1 and gamma 1, both beta 1 and gamma 1 are converging to 0 at an order that, when multiplied by square root n, give us a little OP1. So this debiasing amazingly succeeds in its goal, even when we are doing variable selection on the propensity score. So the idea is you do variable selection on the outcome regression, but you also do variable selection on the propensity score, and then you add the two of them to create a new estimator, which is actually doing the estimator plus the bias estimator, and that succeeds actually to make it asymptotically normal and uniformly so. Okay, so now let's consider, we were not discussing just a small, a one covariate problem, but in general, how do we operate? Well, we have a functional, which is just the mean of G1, which depends on G1 and P. We start with a plug-in estimator, where the eta hat is, for us, is just the G for the moment, okay? But in fact, the eta hat, let me say it correctly. We parameterize the likelihood with a G, pi, the mean, the marginal distribution of x, and the distribution of the errors. And now we just estimate. They start with an initial estimator of our parameter, which is a plug-in estimator, which I write as a function of the whole estimator of theta, but indeed it's just of G, because theta depends on the whole distribution just on G and Px. And for Px, we use the empirical law. This is exactly what we have done before. Let's see here. Oops. Here. This was our estimator. I'm doing just this in it's a fancy way of writing this estimator. All right. Okay. And now what we do is we actually add to our estimator a empirical mean of a function of eta hat and the data, which is exactly what I wrote before. Is this function here, and plus this guy, which actually its empirical mean, when evaluated at any g and any eta, actually is equal to 0. Okay, so this part here is equal to 0, and this part is just exactly the bias term that we had before. But it's convenient to write it in this way, adding this term, because it turns out that this object is a geometrical object that it's, oh, okay. All right, well, okay, so I'm going to go fast. All right, so this geometrical object, I'll show you in a minute, is the key object to the bias, okay, in general. Now, some references for this particular analysis. This theta hat with g hat and pi hat estimated by Post-Lasso is in several papers by Farrell, by Belloni. There's a new paper coming in the Annals where this estimator is used, where the g is estimated by, and the pi are estimated by sparse-sufficient dimension. And then there's a whole literature by Van der Laan and Rubin and Van der Laan and Rose and Van der Laan and all its colleagues, where they do, they essentially select the covariates in pi and g using a superlearner ensemble of machine learning methods. And they actually show that it's all right that you get square root n consistency for the parameter theta. They do it by a method called targeted maximum likelihood, which has some finite sample properties that are better than the one-step estimator that I am describing, but that I am sweeping under the rug because I don't have time to explain it. All right, so I have 5 minutes. Well, 4 minutes. All right. Well, let me just talk about just influence functions. I'll have to skip everything, essentially. All right. All right, now suppose that I have a generic functional, okay? Because that functional that I just described, the ATE, was just one parameter, but there are objects like this in causal inference all along, okay? I can't describe them now, but instrumental variables, logistic regression, everything is of this type. So within observations, we can construct a one-step estimator the same way. We start with a plug-in estimator, and we add an empirical mean of something, okay? The question is, how do we choose that something? What properties should phi have so that this guy, the new estimator, behaves nicely, okay? It converges to a normal distribution. To answer this, we usually decompose this into 3 usual terms. And sorry for those of you that are not mathematicians here, but for statisticians, this should be kind of obvious. Or not obvious, well known. So we take our the difference between the estimator and the parameter scaled, and we write it down as an object that converges to a normal distribution, a center object. Then we write down a piece that it's called the drift, and another piece that it depends on an empirical process. And I don't have time now to explain all the details, but this part here, which is the drift, is where influence functions, which are the objects I would like to explain, come to rescue because they make this drift of the order, a quadratic term. They make this drift to be of the order eta hat minus eta square. And because it's a square term, now we need rates of convergence that are much slower to make this term vanish, okay? So this is the key term that the drift handles. Then the remainder is usually handled by saying that eta hat falls in a class that is small enough so that this is essentially behaving, this guy here and this guy here are behaving equally, and they converge to both to the same place, and it's therefore they are negligible. It's a negligible term. But in fact, what happens with machine learning methods is that usually they do not guarantee, they are irregular enough that they do not guarantee that this term here falls in a small enough class to guarantee that this goes to 0. So, I mean, this is usually handled by, the typical assumptions that one makes to say that this is small is to say that this belongs to a Donsker class. But for that, we need that the size of the set where eta hat falls is small. And usually, with these very big dimensional problems, eta hat cannot be ensured to fall in a small class. So this remainder is a problem. But it's not a problem if we handle it with sample split techniques, okay, with what's called cross-fitting or sample split techniques. So I don't know, I should stop here or should I continue? Good, okay. I can go ahead forever, okay. All right, the drift. The drift is this term here, but just let me show you what the issue is, what the intuition is. So here we have a function of eta hat, a function of eta evaluated at eta hat at an eta. We would like this guy, normally if you think of eta finite dimensional, this would be typically, if the derivative is not 0, it would be like behaving like the derivatives times eta hat minus eta. So what we would like is that that term here acts like the derivative of theta of eta, so that times eta hat minus eta, so that it kills this guy, and what's remained there now on a Taylor expansion is a second order term, okay? So that's exactly what influence functions do for you. This object here, which can be rewritten in this form because this integral, this object here, if we take it means 0, we can add this guy. You see, we have here a difference in the direction, p eta minus p eta hat, and objects that act like derivatives, first-order derivatives of functionals in this direction are, in semiparametric theory, they are called influence functions or gradients of the parameter. And the parameters that have those objects, for which those objects exist, are called regular parameters. But when we choose phi to be the influence function, then the drift turns out to be of this size. And now all we need is a convergence rate of eta hat minus eta at n to the minus a quarter, not n to, we can have eta hat converging at much smaller rates, usually attained by Lasso and most of the machine learning methods. So, I don't know, what else should I say? Well, I should say that for the estimator of ATE, this function here is precisely the influence function of this object, and the debias estimator, the drift, is of this form. What's interesting with the drift is that it's a pi minus pi hat, g minus g hat. It's a product of, it's an integral of a product of two differences, which we can Cauchy-Schwarz. If this guy is bounded away from 0, if pi hat is bounded away from 0, we can Cauchy-Schwarz. And now we get the product of these two terms. This is essential because now what we need is that this guy goes to 0 in probability. But now what's interesting is the feature that it's called double robustness, which is now we can have hat converging at a very small low rate to pi, at a slow rate, so long as g hat converges at a fast rate enough to compensate, okay? So now what's interesting about this particular structure and this particular problem is that we can have one of these functions very, very wiggly, very unsmooth, very, very unsmooth, And we will be fine so long as the other one is smooth enough that we compensate. Okay, that's what the double robustness property means. And for example, well, if pi hat and g hats were post-lasso estimators and the true models were sparse regressions with number of coefficients s pi and sg, now the drift will be roughly like of order, each of these guys is of order square root of the sparsity divided by the square root of n times some log term, which essentially means that the drift will converge to 0 so long as the product of the sparsities is less than or equal n. But you see, we can have one of them non-sparse, very non-sparse, so long as the other one is sparse enough that the product is less than or equal n. That's the nicety of double robustness. So, well, I don't know. I think I'm going to stop here, sorry. All right.
Well,
yeah, well, I can go to the conclusion. Yes, I can go straight to the conclusions. I had a lot, but all right. So the conclusions were that naive methods may fail, not always, because it depends, of course, on which particular estimator of the nuisance parameters we use and the smoothness assumptions and so forth. But in these very high-dimensional problems usually fail. Certainly they fail with lasso. Influence functions offer a general debiasing strategy. Cross-fitting alleviates the smoothness requirements that impedes the self-bias from overfitting in the remainder term, the one that I have not been able to talk about. And I was going to also talk about the parameterizations that yield double robustness. This double robustness business is not a coincidence, okay? There's a lot of structure to it, and it's useful to have it. I was going to show with the semi-parametric logistic regression problem that in inappropriately chosen, the natural parameterization would yield an estimator that is not doubly robust. But using a particular parameterization with log linear models, it does, and it alleviates more smoothness requirements. It generates an estimator that is asymptotically normal under larger set of data generating processes. So then the last part that I did not talk at all is the part that is the ongoing research on higher order influence functions, which is essentially, remember I said the first order influence function kills the first term of the Taylor expansion. The higher order influence functions are aimed to actually kill the larger terms of the Taylor expansion. So, you know, there's a lot of work, interesting work here. It's basically debiasing by the use of higher order influence functions. When the smoothness requirements for the first order influence functions fail, okay? Because as I said, there are conditions for the first order adjustment. If you remember, I said the product of the sparsities has to be less than or equal n. But what if it's not, okay? Then you have a bias term that is of bigger order than the normal term, than the OP, you know, the asymptotically normal term. And it's obviously inefficient because the bias is larger than the variance. There should be a way to compensate, and that's what higher order influence functions do. Okay, they try to accommodate so that they compensate for the bias.
Well, thank you, Andrea.